So today, we're just going to finish volumes up. I'm just going to, I guess I should start with today. I have no witty thing to add on the end. I'm ready to go on vacation. How about you? All right. So typically in mathematics, it's a good idea to define something and then work from there. We are going to do it backwards. We've already talked about how to find volumes by revolution, but we never actually defined volume. Oops. Okay, so today I'm just going to give you a definition of volume and then show an application in terms of finding the volume of something that isn't given necessarily by rotating around an axis. So we're going to see if I can draw something more complicated than a parabola today. It's going to be my honest attempt at drawing something in 3D. I apologize in advance. Okay, so far so good. This is top half is an orange. Okay, now. I'm working it. We're getting somewhere here. Let's see. I hope I got my. I definitely need like a little sort of a cheat sheet here to help me out. Oh no, I don't want it to connect down there. I want it to connect over to the end. Okay. Got that. Now we need we need the okay, we're doing good. I'm going to make it through this. I'm going to survive. Ooh, it's already starting to look a little nastier. Okay, now here we go. Just give me a second here. Okay. So I'll tell you what I'm attempting to do here. Okay, there's some bizarre figure. Okay. What's that? You agree with the bizarre part? Is that what okay, good. Okay. It does, yeah, actually clay would have been good for this. So you have some figure. Okay, and we've had nasty figures before. Remember we took those weird regions that we revolved around the x-axis, right? Okay. Well, this is something where it's certainly not given by revolving around the x-axis. I mean, this is just some jacked up piece of clay or something. Okay? But let's say we wanted to find the volume of it. Well, this little piece in the middle, this is supposed to be some, imagine if you took a plane, right? Nice flat plane, and you cut right down through this thing, say perpendicular, right? Say this is all going around the x-axis somehow. Okay. I just put down a plane. cut right through this sucker. Okay, I'm going to just get it when you take your piece of clay and you cut down with it, right? You're going to get some weird region that looks, somewhat like this. Okay, but it's just a region, right? It's not a volume. It's just an area. Okay. Now, let's say I take that area I get, that cross section, and I start expanding it. Okay, just a little bit. Okay, say, well, how much should I expand it? Let's say I expand it by delta x. Yeah, by some amount, some little amount. Okay. The volume of this piece, where now, mind you, let's say I'm doing this regularly. The area, it's the same. The cross section, when I expand it, it's just the same cross section over and over and over again. Right? It's like you took a cross section and you pushed it through space, okay, a little bit, and you just expanded it. When I say that, do you have any idea what I mean? Okay, imagine if you took a circle, right, and you dip it into the soap. Okay, dip it in the nice soap, and you pull it out. Right now, there's a film on the inside of it. Okay, and then you start doing this. Right? What happens? You make a bubble, right? But what kind of shape do you get? It kind of, well, you start as a circle, but as you go through the air, it turns into a cylinder, right? Think about when you were a little kid. You ever have one of those? It's also usually circular, okay? And it was wrapped up, a little tie or something. And when you let it go, it would pop out like a snake. Or like a slinky, exactly, right? Okay, so this pops out. Well, you could think about it is you've taken a circle, okay, and you pass it through space. Okay, but instead of it just being the one circle, everywhere it hit, you kind of leave a residue, okay, of something. Okay, and so you get this figure, right? Or in the old days, when you would move your mouse around the screen, you could actually see the trail of your mouse hanging on the board. Okay, imagine that, right? Except the trail never disappears here. Okay, you move it through, and you just, whatever it went through, right, you get that whole thing. Okay, we're doing the same thing here. I take a cross section, just a flat region, and now I push it through space a little bit. Right? How little bit? Well, delta x, whatever my delta x is, right? Some small bit. Right? And the volume, right, of this thing where I've taken one cross section and pushed it a little bit is the area of that cross section. Okay, so this here is the area of the cross section times, right, the width of that cross section, however long I did it. Okay? And if you think of a cylinder, you already know this formula. What's the volume of the cylinder? Well, you take the area of the circle times, right, whatever the height of the cylinder is, okay, which is how long you've passed it through space. You start with the circle and pass it through space for h. The volume is the area, pi r squared, times the delta x. Here the delta x is actually h. And there's nothing special about a circle. Right? If you took a square, you take a square and you pass it, oh dear. Oh my. Well, I'm trying to pass this through space. I'm just trying to make a rectangular parallelepiped, right? Just, a block. Okay, what's the volume of the block? All right, well, it's the area, say it's base times height, right? It's the area of the rectangle times the length of that rectangle, right? How long you pass that cross-section through space. You believe that? So the same thing holds when you just take any cross-section, right? You take any region. It has an area. You pass it through space for a certain amount of time, whatever amount of time that is, right, measured by the distance, okay, delta x. Your volume is just the area times that distance. Okay, so of course this isn't giving you the exact volume of the region of this actual figure, because what I did is I took one cross section, say in the middle, and I just expanded it. I didn't care if it actually met, right, if it actually followed the regular volume, right? It was the same way when we were doing areas. Right? When we broke things up, we would choose a rectangle, we would choose a height, and we'd draw that rectangle, and we would take this. This gave us an approximate area under the curve, right? But we missed a little bit because, well, okay, we picked that point and we made that the height. Okay, we're doing the same thing here. Okay, we're picking some cross section, and then we just take that and expand it out. And it may be higher than the region, or it may be lower than the region, around it. But it's an approximate volume. Right? How are we going to get the exact volume? Integration must be built in here somehow, right? Well, just intuitively, okay? You take a bunch of these cross sections, you build a bunch of these sort of generalized cylinders, right? And then you add them up, and that'll give you an approximation. How do you make the approximation better? Use smaller ones and more of them, right? How should we define volume then? What's that? Integration, right? Okay, so what was the integration, right? Well, what if we define, right? So this is define the volume to be the limit as the number of these regions goes to infinity and their width goes to 0, right? Of, well, the area of the cross-section times its width. Okay, now wait a second. The limit, and of course you have to add them up, as the number of these things goes to infinity and the width goes to 0. Right? Of course, you're adding up all the volumes that you get. And each volume is equal to, well, let's say if I choose a point xi, then that'll be the area of the xi cross-section. And let's say I make all my width the same. Right? That's the volume of each of these little pieces, right? The area times the width. But this is exactly the definition. Say if we're going from A to B, this is exactly the definition of the integral from A to B of the area function dx, where what this function does is it tells you at any point x, right, take the perpendicular plane to the x-axis and get a cross-section, and look at the area of the resulting region you get, right? The resulting cross-section. Okay, this is the definition, right? That's how we define the definite integral. So we just define the volume this way. Now, what have we been doing all this time? When we did all these shell methods and disk methods and so forth? Well, with the disk method, we were drawing disks. We were approximating our, say we have our function. Okay. And so we're going to rotate this around an axis. Oops, I guess I can do that one out. Okay, so we rotate this region, say. And what we did is we started drawing which way do I want to draw my disks? Well, see, if I'm rotating around the y-axis, I'm supposed to be using disks, then I guess they should be this way. Yeah. So what I might do is I take a cross section. Okay. What's the cross section? Right. Well, since I'm rotating it in a circle, the cross section is actually a circle. Okay. And what I do is I pick some little height. That can go around. Okay. And I actually build a little disc out of it, right? It's a cylinder. Okay. So I was taking my cross section, right, is actually a circle. Okay, and then of course it builds into a little cylinder. Okay, the area of the circle is pi r squared, and the height is your delta x. Okay. And what was the formula? Well, the formula was, okay, we put the pi on the outside, but let me put it on the inside for a second. Right? Pi r squared, well, here r is, right, whatever the x coordinate is. Pi x squared, right? Remember, since we're going around the y-axis, we're looking at x as a function of y. Right? That's why I don't write f of x squared here, right? This could also be written. This is, and of course, there's some limits here that I'm not writing. Okay. You could also write this as pi. Well, x is f of y, so f of y squared dy. The point is that what we've done already, right, the way we constructed this formula, right, was actually consistent with this definition of volume, right, with what we're doing here. You pick a cross section, and when you revolve around an axis, you're always getting your cross section is always circular. Right? Is that clear? If I take a point and I revolve it around an axis, what does that trace out? A circle, right? That's why my cross sections are always circles. Okay? That's why I'm always getting things like pi r squared, or 2 pi r later on. Okay, now, of course, there was this more complicated problem of what happens when I take this region, say, I want to rotate it around the axis, but instead I move it over here. Right? I move it away from the axis, and I still want to do it. And what happens? Well, what happens is that you end up, right, having to cut out a portion of your circle in the middle. Okay, that's what we ended up. I guess that should be dotted. You lose it. You build a little hole in the middle, right, of your cylinder that you have to cut out. That's what happens if you move things around from the side, right? That's why we had to have this the difference of disk method and the difference of shell method. Okay, you end up having to cut out a little cylinder. Okay, so I just wanted you to see it's everything we're doing is based on a definition, right? And this definition, looks like, oh, where's the pi or something that that we've been getting before, right? When the only difference is here we have the pi. The pi is actually part of the area. Okay, that's where that pi is coming from. It's part of the area, but of course we always just pull it out, because we know that you can pull constants out. Okay, now I want to use this to solve a problem that you don't solve with around a revolution. Kaiwei. It's the thickness, exactly. Yes. So I cut down this, I draw this plane that goes through it. Okay, in principle, this is actually, we're angled here, right? But this is actually the figure you're supposed to get. If you drew a perpendicular line down to the x-axis, right? Or a plane, rather, right? You'd get this weird region. You always cut in a straight, a flat plane, right? And so you get some picture on the plane, right? That's a flat area. And then you just take that and expand it. Okay, just like when you take the slinky and pull it open. Right? Or take a circle and turn it into a cylinder. Take your weird region and turn it into a something. A Willinder. That's short for weird cylinder. so let me draw a picture. Oh dear, this could be bad. So we're going to start with this picture. I might need to look at this. I might need to see this too. Yeah. All right, so let's see. Perspective drawing is not one of my current talents. Okay, so let's... This is actually a circle, but I'm tilting things, so that's why it looks a little weird. Yeah. Would be a circle if you could see that. Okay, and then let's... Ooh, that's kind of bad. Okay, we're going to draw that up there. And let's see, let's get in the middle, and then we'll... So this circle is the base of something, okay, and then it's coming up. All right, and let's see here. So there's a little radius to that circle, and okay, let's see if I need another line in here. I think that. Yeah, so just imagine if the first approximation in your mind. All right, imagine you have this circle on the ground. Okay, but it's a little thick material, and you pinch it in the middle, and you pick it up. Okay, well, that would be too pointy. Okay, so now let's say you use a couple hands, right, or maybe you use your hands, and it sticks to your hands, and you pick it up, and it goes up a little smoother. Okay, so I'm just pulling it up a little bit. It's pulling away from this base circle. But now let's say I do it in such a way that if I draw a cross section. Okay, so I intersect now with a plane. Drop a plane down through this thing, right? I look at it from the top and take a plane and put it down. And what I get when I do that is an equilateral triangle. Okay, when I cut down through the top of this thing, down to the circle on the bottom, I get an equilateral triangle. I apologize. I know. What's that? Not a sphere. Because if you take a sphere, what happens if you hit it with a plane? You get a circle. Right? So this looks like a sphere, except when you hit it with the plane, you get an equilateral triangle. Yeah, so it's coming up to the top. Yeah, exactly right. And it kind of pinches up at the top. Okay, because it's got to make these triangles everywhere. Anywhere you hit it with this plane, you're getting a triangle. Okay? And even an equilateral triangle, right? So if you went to the middle of this thing, right, in the middle of the circle, and let's say the radius of the circle is going to be 1. There's the middle. Okay, so the radius of this circle is 1. If I went straight up, right, and drew the triangle that was, oh shoot, I can't say. I guess, oh, there's your top triangle, right? It's right up at the top. That's your hinge. And there would be your big triangle in the middle. That would be the biggest one there. Right? And that would have height 1. Right? Or height 2, rather, because it's supposed to be an equilateral triangle. So the base is actually the diameter of the circle. You see that? Okay, there's my diameter. Right? Going across through. It's actually going through the origin. I just can't draw it. You see, it's okay. I struggle with certain parts of math too, like drawing. Okay. So we just have this picture, right? It is just this thing that pinches up at the top, and if you drop a plane through it, you get equilateral triangles everywhere. Okay, but it still has a circular base. Kind of weird, I know. But this could happen. And I want to know what the volume of it is going to be. And I want to use this definition of volume. Right? So what that tells me is I need to figure out at any given point here, right, what's going to be the area of this cross section, which is an equilateral triangle. Okay. So first, let's draw this maybe in more 2D style. Maybe that will be helpful. Yeah, why don't we do that? Yeah, you do that, Adam. Okay. So the base is a circle. We're very happy with this, right? And without loss of generality, this is, oh, by the way, this is a very good mathematical expression. Without loss of generality, right? It means you can do whatever you want. Right? No, of course, what is it saying, right? If you have an object, we've already said it, the volume doesn't depend on where it is, right? You can turn it, you can move it. The volume doesn't change. So you might as well put it at a spot which is convenient for calculations, right? So I'm going to center my circle at the origin. Yeah? So that's what I say. Without loss of generality, we may assume the circle is centered at the origin, because it doesn't change anything. Very good math expression. Okay? And it has radius 1, so I know that the equation of this thing is x squared plus y squared equals 1. Okay? And so if I just solve for the positive root, right, just the top half of the circle, I get that y is the square root of 1 minus x squared, right, for the top half. Okay. Now, how am I going to get the area of this equilateral triangle? Well, let me draw an equilateral triangle. Beautiful. Now, what I can do is just arrange things so that this direction, say, is measuring the y coordinate. So if that's 0, then this distance is y and that distance is y, for whatever the y coordinate is. Right? So if I take this nice equilateral triangle, I know that it breaks up as a y and a y. For whatever, I mean, I can move this thing forward and back, right, and the y changes. And then, of course, the total length of these things is 2y. And then what's the middle? Y root 3, right? By the Pythagorean theorem, it's 4y squared minus y squared, which is 3y squared, and then you have to square root it. So you get the square root of 3y. And so the area of this triangle is a half the base times the height. Okay, and well, there's two of these triangles, right? Or just one of them. In any case, you have 2y times root 3y times a half. So half times 2y times root 3y. And so let's see, the 2.5 cancel, and you get root 3y squared. Alternatively, you could have used the formula we proved at the very beginning of class. Right? It's an equilateral triangle, so what are these angles? 60 degrees, right? So we know that the area could also be given as a half. Well, you just take the two adjacent sides, so and product them, so you get half times 4y squared times the sine of 60 degrees. right, or pi over 3. And that's root 3 over 2. So those cancel with that half and the root 3 over 2. The over 2 cancels with that 4. Again, you get root 3 pi y squared. So either way. Okay, so you know that the area of a cross-section is root 3 y squared. Okay. And if we want to put that into x's, let's worry about the limits later. Right, so let's see, we're going to have a root 3y squared. And I want to do it with respect to x. And I can put it into x's by saying, oh, actually, I know what y squared is, right? It's 1 minus x squared. So root 3, I pull the root 3 out. 1 minus x squared dx. And now what are my limits? Well, I have to go from one end of the circle to the other. And the circle goes from minus 1 to 1. Right? So on the x-axis, right, we're going from minus 1 to 1. Same thing here. Okay, so if computing the volume of this thing just comes down to actually computing this nice integral. No? Okay. Oh, yeah. Okay. Okay, so let's, well, we'll just quickly compute it out, and then we'll have the area, or the volume. So, okay, the volume is root 3, integral from minus 1 to 1, 1 minus x squared dx. And now, you can see I move faster because I feel like I'm on firm ground. I know how to do math. Let's see here. So x minus a third, x cubed, right? Actually, you know what I would want to do is I know this thing is going to be symmetric, right, about the origin. So I actually am going to turn this into 0 to 1 and put a 2 out front. Because then I don't have to evaluate at minus 1. And I just get 1 minus a third, which is 2 thirds. So 4 root 3 over 3. It makes me feel better when I can do arithmetic. And, you know, to some extent, I think you can make the case that actually solving these integrals should fall under the name arithmetic. Okay, I know that sounds kind of mean, like all you're doing is arithmetic. But I like to enlarge the definition of arithmetic to be any calculation which is essentially formulaic. Now, okay, some of these integrals are so complicated to work out that you don't really want to call them formulaic. But the power rule ones, right? That's essentially formulaic. And just like doing 1 plus 5 or any other arithmetic problem, one can make mistakes doing arithmetic. It's okay. It happens. You know? Just think. Some people make arithmetic errors adding up columns of numbers, and some do it in calculus. It's okay. It's all the same. You know, it's just I'm just trying to make you feel better somehow. I feel so bad. Okay. I'm going to cook up some problems for you guys to work on. Well, okay. I know it's spring break, okay? I'm not going to try to make you, bust your buns over spring break on this stuff. But I'll put it up there so that if you want to over spring break, you can. And then, of course, you'll have the following week to do it as well. Okay? So I'll put a bunch of problems on here. I can only hope, and you can only hope, that I'm able to explain what region I'm talking about better than I did right now. Honestly, I think on these, the hardest part is actually figuring out what in the world you're talking about. Yeah, so that would be a really excellent final project. teach Adam how to draw. Okay. Let's see if I... well, now I didn't like this one because that's kind of a stupid one. Let me... What's that? Oh, I thought I heard something. Actually, I did the stuff I wanted to do. Should we just call it early? Is that what you want, Dina? Okay. Have a nice spring break.